طيب بسم الله الرحمن الرحيم. So we started to talk about chapter 3. We talked about message authentication codes and hashing techniques. And today, inshallah, we are going to start public key cryptography. So for public key cryptography, it started in the 70s with the first public key encryption, or it's not encryption, public key technique, which is Diffie-Hellman. Diffie-Hellman is not to be used for general purpose encryption, as we will see. It's used for a particular job, which is key exchange. Okay, but it's not to be used for general purpose encryption, and we'll talk about why. Then after that came the revolutionary technique in that category, which is RSA. So RSA is a technique that was developed by Rivas, Shamir, and Adleman, obvious طبعا. And that's the one that's actually the most common. And of course, Al-Gamal, Murad Al-Gamal, he's Egyptian. Murad Al-Gamal also developed another technique in that category, which is also very, very famous. So we'll cover these techniques as part of this class. These techniques are based on mathematical functions rather than on simple operations like permutations and transposition, as we have talked about before. These are based on straightforward mathematical derivations. And that's why you will see that today's lecture is heavily math dependent. Okay? So we're going to go through lots of math this lecture. Okay? It's asymmetric in the sense that we are using two keys. We are using two keys, one public and one private. One to be shared with everyone, and the other one, it identifies the source of the information. And that's why we said that to use public key for encryption or for confidentiality, typically what you would do is that you would use the public key for encryption to send confidential data to a particular entity. However, when it comes to authentication or message authentication, typically what happens is that the sender embeds his or her own private key in every message by using this private key to encrypt, this time the hash, right? So we encrypt the hash of the message using the private key of the sender, and we'll talk about this. ماشي? There are very common misconceptions about public key cryptography. We hinted about that last time. So one of them is that public key encryption is more secure for cryptanalysis, more than symmetric keys. And that's a misconception, because when it comes to the same size of key, let's say, symmetric encryption is more efficient in terms of complexity. So that's why you will see public key cryptography is typically used not for encrypting the data, although it's possible, but in many cases it's used for encrypting hashes or digital signatures and things like that. Okay? The other misconception is that public key encryption is a general purpose technique that has replaced conventional encryption or made it obsolete. That's also a misconception, because we said that the more common usage for public key is more on the side of the authentication, message authentication, or key exchange, as we will see today. Although encryption is possible, but we tend to actually use symmetric keys for encryption more commonly, okay, because it's less complex. There is also a feeling that key distribution in the case of public key is trivial, or it's zero cost, and that's also a misconception. It's not to say that it's zero cost, because typically you would have to have all the public keys for everyone in the system in order to be able to communicate with that device or that entity. So we cannot say that the key exchange for the case of public cryptography is zero cost, or the cost is trivial. There is a cost. It's less. It's significantly less compared to symmetric keys, of course, because for symmetric keys, as we will see, and we will talk in the next chapter, symmetric key encryption requires a significant cost when it comes to key exchange. And that's, of course, because of the fact that because it's symmetric and it has to be shared between the two entities communicating, in order to share that key, you need secure channel to share that key. So it's a chicken and egg problem. So I use it for securing a channel, but in order to share that key, I need a secure channel. Okay? So so they break that loop by actually sometimes using public cryptography for key exchange, but still use symmetric key for confidentiality and for secure communication. واضح كده؟ Okay? So this is the security model. We've talked about security models. So this is the security model that describes the public cryptography. So typically, for the case of encryption with public key, each node would have a chain of public keys. Okay? So this is Bob's public key, this is X public key, this is Y public key. So you typically have a chain of public keys, which sometimes it's big depending on how big the system is, right? And you use the public key to encrypt the message that goes to a certain entity. So you use the public key of that person. So this is Alice and this is Bob. So you use Bob's public key to encrypt the message going to Bob. And then Bob would use his own private key, right, to decrypt that message. So, of course, as we can imagine, there is the condition of reversibility when it comes to some of the public key cryptography. Not all of them. We'll talk about which ones that fulfill the condition of reversibility, because not all of them, they do that. But when it comes to using techniques like RSA, Al-Gamal, or elliptic curve, and these kind of techniques, you can use either the public key or the private key for encryption. The other one would be used for decryption. So you can use either, okay? And if it's reversible, then what you will get here is the original message if you decrypt using the private key, okay? For encryption with the private key, and that's typically used, as we said, for IBA. Encryption with the private key for use for a? For authentication, for message authentication. Okay? So in that case, Alice would use her own private key to encrypt, in that case, not the actual message, but typically the hash or the digital signature, okay, resulted from the message itself. واضح إن المحاضرة اللي فاتت has not been. Okay, so the private key is used in that case to encrypt the hash instead of the message itself. So in that case, Alice would insert that private key by encrypting the hash and send it to Bob. And in that case, Bob would use the public key for Alice to decrypt the hash, okay? And then we perform the normal hashing on the message itself. We'll see that. We'll see that scenario. And then we compare. Okay, so we'll see that scenario in detail. Yes. Al-hash, decrypt the hash, not the message. So we'll see that scenario in more details in a minute. Yeah, okay. طيب. So, public key systems are characterized by the use of cryptographic type of algorithm with two keys, طبعا, of course. So that's the first thing that distinguishes public key cryptography from symmetric keys. For symmetric keys, we are using only one key for encryption and decryption, but for public keys, we're using two keys. Depending on the application, the sender uses either the sender's private key or the receiver's public key. Okay, because he does not have the receiver's private key, of course. Okay, or both to perform some type of cryptographic function. So the use of public key is actually is commonly for these types of usages. So it could be used for general encryption and decryption, and for that particular usage, reversibility is a must. You have to have reversibility. Okay, so you have to get the original message when you decrypt. So when you encrypt using the public key, when you decrypt, you get the original message. Okay, because in some cases it's not valid. Reversibility is not valid, and we'll see that. So for digital signature, the sender signs. Yeah, digital signature sometimes. And I noticed هنا digital signature مقصود بها originally يعني it originally means the hashing part, but sometimes digital signature implicitly means message authentication. Okay, and as we will discuss in this lecture later, there is the DSS or digital signature standard. Okay, it actually includes message authentication. Okay. But the word digital signature, if you see the original definition, digital signature means that you create a signature of the message, which indicates the hash, okay? But it does not necessarily include message authentication codes. But very commonly in this book, it is actually used for both, or it indicates both, the digital signature and the message authentication.
It's interesting that actually digital signature was reason for public key crypto system.
Right, originally.
Because Diffie-Hellman were not the first. The first, by the book, were British Secret Service in 1970.
Yeah.
However, there is a document declassified from 1962 that shows that NSA was using public key cryptography for PALs, permissible access links.
For what?
PALs.
PALs, PALs,
permissible access links that are used to authenticate the access to the nuclear weapon.
Wow, okay.
So even in 1962, something like public key crypto system was in use among the intelligence.
Yeah, of course. When it comes to intelligence service, they are far advanced, far ahead. Yeah, so, yeah. The last usage is key exchange. For key exchange, as we will see, reversibility is not necessarily a condition, or it's not needed, as we will see. And Diffie-Hellman is one of the most common when it comes to key exchange, as we will see. Okay. So to summarize the public cryptography techniques and what they are used for, we will see that RSA is general purpose, which means that it can be used for any of them. Okay, Diffie-Hellman cannot be used for something other than key exchange, and even for key exchange, as we will see, there is an issue when it comes to man-in-the-middle attack. It's very possible in the case of Diffie-Hellman, and we have to do something about it. So we have to use Diffie-Hellman together with another authentication technique in order to avoid man-in-the-middle attack. Because otherwise, man-in-the-middle attack is a big issue for the case of Diffie-Hellman. There is the digital signature standard, which is done by FIBS. And this can be used for digital signature. So it can be used for message authentication. And of course, elliptic curve, which unfortunately we're not going to go through as part of this course. It's also a general purpose technique which is similar to RSA. In fact, elliptic curve is one of the hot topics that many people are studying nowadays, recently.
The quantum resistance.
Okay. Right. Starting from here, we're going to have to go through some math because, as we said, these techniques are heavily dependent on math derivations, unlike all the permutations and transpositions which we have talked about before. So the public cryptography is based on straightforward math. So this branch of mathematics is referred to as modular arithmetic. So the mod is based on the fact that the modulus of any number. So if you have any number like x mod y equals to, so here the answer is actually the remainder of x divided by y. Okay, so this means that x now can be represented as a linear operation of y, and the answer to this is r. So this r is actually the remainder of x divided by y. So that's obvious, we know that. So for example, so if we say, for example, 8 mod 7, what is the answer? 1, right? So because 8 is actually 7 plus 1, right? So 1 is the remainder, so this is 1, okay? And this I, we call it the quotient or the divisor of x, okay, when it comes to a y, okay? Type. So that's straightforward, so we know that. That's easy, okay, we know this. And now the more important is the properties when it comes to this mod function, the summative and the multiplicative properties, which are very, very important, okay? So we know that x plus y mod n, for example, this is equal to x mod n plus y mod n. But the problem is that when you get this summation, the summation might be above n. So you have to say this whole thing mod n again. Okay? So that's the summative property. This is very important. Okay? Similarly, the multiplicative property, which is very similar. So x times y mod n, again equals to x mod n times y mod n, and all of them mod n. واضح كده, okay? So this multiplicative property, for example, is very, very important, and sometimes it saves us a huge amount of time when it comes to calculating some mods. Like, for example, let's say if I give you 10 mod 7, let's say, what is this?
2.
This is
2.
Sorry, 2 mod 7. What is this? 2. If I tell you بقى هنا 2 to the power 90,000. What is this? Calculator? Even the calculator would overflow if you do this. Right? Okay, so how do we do this? How do we do this? This is it turns out using the multiplicative property, an exercise like this is very easy, because you can simply say that 2 to the power 90,000 is in fact 2 to the power 3 multiplied by 30,000. Okay? And this is mod 7, right? So using the multiplicative property, you can get the mod inside, right? So it becomes 2 to the power 3 mod 7 all to the power of 30,000. Mod 7. What is this? What is the answer now?
So this is
117.
Which is?
1.
1. So the answer is simply 1. So this 30,000 did not affect, because actually 8 mod 7 is a 8 mod 7 is a is 1. 1 to the power of 30,000 is 1. Mod 7 is also 1. So the answer here is 1. Right? So this very complicated problem, it turns out to be very, very easy when you use the multiplicative property. Okay? So in other words, we come back to the next level where we discuss the factorization of any number. Factorizing any number means that we need to find all the divisors of that particular number, all the divisors of that particular number. So let's try a number. So n, we need to represent n in terms of the multiplication of any set of numbers. Okay? So this means that we are factorizing n. Okay? Bear with me, because we'll use that later on. Huh? So until now we are just reviewing some math. So like for example, if I tell you 160, how do we factorize this? We try to get the lowest divisor, and we can use 1. Of course, 1 is part of any. 1 is a factor for any number. We know that. And then we can use 2, right? It's divisible by 2, so we can 2 by 2, it becomes 80. By 2, it becomes 40. By 2, 20. By 2, 10. By 2, it's 5. And then we cannot use 2 anymore, so we say 5. So these are how we factorize a number. Okay? Later on, we'll talk about the properties of these numbers. So next, we need to know what is the property of these numbers. Okay? But this is how we factorize any number. Okay? Which means that this is a 2 to the power 5 times 5. Okay? This is how we factorize a number. Type. What is a prime number? A prime number is a number that is factorized by itself and the 1. That's it. Okay? So Pi, it's a prime number if we factorize it and we reach to a 1 times Pi. And there is no lower divisor that divides Pi. Okay? 2, is it a prime number?
Yes.
Yes, because it's only 1 and 2, right? 3, 5, 7, 11, 17, okay, and so on, right? So these are all prime numbers, okay? Type, which means that these numbers, as you can see, these are prime numbers. So it turns out the theory is that any number n can be factorized using set of prime numbers to the power, let's say, xi. Okay? So you can have any number factorized using set of prime numbers. Okay?
Yeah.
That's what we typically do when we factorize a number. We try to use the lowest prime number, which is 1, and then 2, okay? And then we try 3, and so on. This is how we do it. Of course, in cryptography, we don't use these low numbers, as we will see. Type. So that's this property. So this property indicates that factorizing any number using the prime number. So any number can be factorized using prime numbers. The worst case, if it's on its own a prime number, so it can be factorized by itself under 1, right? So it applies. Now we come to to the nitty-gritty stuff. So now we talk about the greatest common divisor. Greatest common divisor between any two numbers is, from the name, it's the greatest divisor that divides both numbers. Okay? So let's say, so we say that 160 is in fact 2 to the power 5 and 5, right? So imagine if we have another number that divides like this, مثلا 5 times let's say 3, يعني 3 and 5, يعني 3 and 5. And this is طبعا 15. So what is the greatest common divisor between these two? 5. Okay? So if it's 30, for example, then it's 2 times 3 times 5, right? So in that case, what is the greatest common divisor? The greatest common divisor between 30 and 60 is a 5 and 2. So it's 3 times 5 times 2, right?
Yes.
Right? صح? So 2 times 3 times 5. Okay, so what is common between the two? The 2
And the 5.
the 2 here and the 5. Okay, so 2 times 5 is 10. Okay, so you find the common divisors between the two numbers, and the greatest common divisor would be the result of these. So we have 2 and we have 5, so it's 2 times 5, which is 10. Okay, طبعا later on we will have في حاجة غلط؟ شايف في حاجة غلط؟ ممكن في حاجة غلط أنا ما
30 and 16 is 10.
Which 16? It's 160.
16 إيه؟
It's not 16.
160 sorry.
160, yes.
شفت؟ قلت لك أنا ممكن أنا by the way I took some antihistamines so I'm kind of low now. 160 okay, so 160 sorry my
From the beginning, it is 2 to the power 5.
yeah. So 30 and 160, so the greatest common divisor in that case is 10, right? So we can do it manually for low numbers, but we will discuss later on a systematic way of how to do this greatest common divisor systematically using a certain procedure. And this procedure can be computerized very easily. Okay? طيب. If GCD of any two numbers is 1, okay, this means that these two numbers are relatively prime. And relatively prime here does not mean that A is prime or B is prime. Does not necessarily mean that. But both of them, the greatest common divisor for both of them is 1. Example, if we say مثلا 160, which is 2 to the power 5 times 5, and let's say 7, okay, which is 7, right? So is there anything common between them? So in that case, the only greatest common divisor is 1, right? 1 divides anything. صح كده? So in that case, these two numbers, and as you can see, 160 is not prime number, right? 160 is not a prime number. 7 happens to be a prime number, but that's not a condition. So the A and B, they don't necessarily have to be prime numbers. But the greatest common divisor is 1, meaning that they are relatively prime.
Co-primes, right?
Or co-primes, yes. Okay? ماشي كده؟ طيب. Now let's talk about the most important step. So all of this is preparation for this. What is addition of n? Okay? Addition of n is the number of divisors, or not number of divisors, I shouldn't say divisors, the number of integers between 1 and n minus 1, okay, such that these numbers they are not divisors of n. Not divisors of n. Okay? Not divisors of n. Okay? Like, for example, if we say 160, what is the quotient of 160? So we have to go for all the numbers from between 1 and 159 that are not divisors of 160. Okay? So obviously the 2 is a divisor and the 5 is a divisor. Okay? So all the other numbers are counted, are to be counted, and then this is the quotient of 160. And again, we will try to find a systematic way of calculating this. An extreme for the quotient is usually referred to as phi. So phi of n, okay, if n is a prime number, what is phi of n?
0.
No, بالعكس.
No numbers between 1
بالعكس. بالعكس, all of them.
Yes.
So it becomes actually n minus 1. Because the only thing that divides, yes, that are not. Yes. Okay? By the way, this is the main theory based on which the public key is made. We'll talk now. Okay? So this is the quotient of a prime number. And we also we can also use the multiplicative property for the quotient. So quotient of Q times P is actually the quotient of Q times the quotient of P. Okay? So if both Q and P are prime numbers, so it's simply Q minus 1 times P minus 1. صح كده? So the quotient of P times Q is actually P minus 1 times Q minus 1. Okay, so the multiplicative property also applies here.
Prime or even relatively prime. Correct?
If they are relatively prime, no. We didn't say that. No, because relatively prime, that doesn't mean in each of them is prime.
Yes.
So if you say that the quotient of one of them and one of them is not prime, then it's not n minus 1.
Yes.
Okay? Following so far, it's going to get even worse. Huh? So if there is any issue here, you need to raise it. Okay?
It's quotient, it's not quotient.
Yeah, here it's quotient. Sorry, it's quotient. Sorry, not quotient. معلش, my bad. My mistake.
No, I never learned this in English, so...
لا. The quotient is the divisor. What we mean here is the quotient. Sorry, not the quotient. I'm not sure if the people here are following. So now, we talk about RSA. So the RSA is based on the fact that it's based on 6 different steps. Okay? So step 1, each node locally, and this is the key. Not the key, this is the important thing here, is that each node locally selects 2 prime numbers. Locally. And these are not to be shared. Those 2 numbers are not to be shared. Okay? And that's very important. And that's what actually simplifies the key exchange compared to symmetric key. No, these are huge prime numbers, by the way, in the order of 300 digits. Typically 300 digits. It's meant to be like this. And I will tell you why. Okay? Number 2, calculate n, which is Q times P. And which means that n cannot be factorized because these are prime numbers, right? Mm-hmm. These are prime numbers. So you cannot factorize n except using these 2 numbers. صح? Right? And that's again the main idea of this algorithm, because if I give you P and Q, everything will be easy. You can do all these steps very easily. But if I give you N, and you should guess what P and Q are, mathematically, you have to go through exhaustive search. Remember, these are the only two numbers that factorize N. And I will give you N in the next slide. I will give you an example for N, and I will ask you visually to try to guess what P and Q are. So even for low number, you will not be able to find it out easily, okay? So imagine بقى if N is in the order of 300 or 400 digits, okay? So this will be a very, very intensive job. And that's very important بقى, okay? If you cannot find P and Q, the calculation of totient N becomes also a mathematically برضو not straightforward, okay? Because the totient of N is again based on these two numbers, okay? So totient of N is P minus 1 times Q minus 1, right? Again, you will not be able to find that easily. واضح كده so far? So that's step number 3. Okay? Now, we need to select, again, until now, we are local in one machine, in one node, يعني. We need to select an integer E, okay? E. And E here is relatively prime with the totient of N. Well, if you know the totient of N, guessing E is not that difficult. You have multiple answers here, okay? Here you have multiple answers because you have set of numbers that are relatively prime when it comes to the quotient of N, right? But that's if you know the quotient of N, which requires the fact that you have to know P and Q أصلا, okay, which you don't know, okay? So E is relatively prime to the quotient of N. Remember, not N, quotient of N. Okay? طيب. We're not done yet. So now we need to calculate D, and this step is actually for reversibility. This is بقى for reversibility, and we will see how. ماشي? So the first E is actually this is the public key, okay? And the condition here for the public key is it has to be a relative prime with the quotient of N. طبعا, of course, we have multiple, okay? We have multiple values for that. And D بقى is the multiplicative, we call it بقى multiplicative inverse, okay? The multiplicative inverse of E mod quotient of N. Okay? Sometimes they refer to it as E minus 1, okay? But remember, this is modulus quotient of N. Again, the quotient of N is not known easily. ماشي? So now we're done. So number 6, the public key becomes E and N, and the private key becomes D and N. Okay? So again, the D is the private key, can be calculated systematically, okay, if you know the quotient of N. But in order for you to know the quotient of N, you need to know P and Q. You need to guess P and Q based on N. واضح? And this guessing mathematically is very intensive job. Supposedly, of course, you can do it using exhaustive search. And mathematically, this is probably the only way you can do it. You have to do exhaustive search. Remember, these numbers are in the order of 300 or 400 digits. So good luck trying to do exhaustive search for this amount of numbers. واضح؟ Okay. طيب, so this is the, once we have the public key and private key, خلاص our job is done. But remember here, for encryption with the plain text, what we do is that we get the message itself in the base, and we put the exponent as the public key. So the message as a plain text, of course, we can convert the message to a number, big number, right? And we put the exponent as the public key modulus n. Imagine. So this will result in the ciphertext. We get the ciphertext again, and we put the exponent as d. Okay, again modulus n. We know n, n معروفة. For both sides, n is known. Okay, what's not known again is p and q, resulting to n. Okay. So if we do that exponent, we get the original message. This is the private key. So this is a typical encryption scenario. Okay. واضح كده? So any questions so far? So the first thing we need to do here, we know that there are two conditions for this RSA algorithm to be valid. The first one is robustness, and the robustness is coming from the fact that factorizing n to p and q is mathematically a very intensive job, and the only way you can do it is through exhaustive search. Okay? Number two is reversibility. So we need to see how these steps can lead to reversibility. In other words, if we do this ciphertext to the exponent of d, will that really lead to m or not? And if there is any condition for that, we need to know what this condition is. Okay? So the proof for this is systematic. So we know that c to the power d mod n, okay, this is in fact, what is c? C is m to the power e mod n, okay, and this whole thing is to the power d, right? Mod n. Okay, so what is this? So this is supposed to be m. This whole thing is supposed to be m. Okay, so how can we get this? So of course, using the multiplicative property, we can get the d inside and get the mod outside this. So it becomes m to the power ed, okay, mod n. Okay, so we know this, right? صح كده? So what does it mean for the ed, the exponent to be ed? تعال نشوف كده what is ed. So remember, ed, this is the e is the public and d is the private. Okay, now they are multiplied by each other. Okay, but we need to see whether this will lead to m or not. So let's see. Remember, how do we select d أصلا? We selected d based on the fact that de mod the quotient of n, the quotient, not n, the quotient of n equals to 1. And what that means is ed can be represented as a linear combination of the quotient of n and the remainder is 1, صح?
Yes.
Okay? So which means that m to the power ed becomes m to the power of some integer I multiplied by the quotient of n plus 1, which is the result of the mod, right?
Yes.
Okay, and this is mod n, right? Okay. So far, so good? Okay, so if we get the m outside, if we get this one outside, so it becomes m okay, multiplied by m mod n طبعا, multiplied by m to the power the quotient of n multiplied by I, all mod n. Okay?
Stupid question. I mean, I learned math very long time ago and not in English. Is it quotient or totient? Because when I was doing Euler
Sorry, yeah, it's the totient, because I said, I've been saying totient. Thank you for correcting me. لا, you're perfectly alert, يعني. I like that. I need that from time to time. I do mistakes. So, okay, so now it becomes like this. So now we have a very important theorem, which is done by a mathematician called Euler. Okay, so Euler has a very important theorem. The Euler theorem is the fact that any number to the exponent of totient of n mod n is 1 if and only if m, the greatest common divisor for m and n, is 1, if they are relatively prime. So if m and n are relatively prime, okay, then m to the power of totient of n mod n is 1. Okay? So that makes this part easily 1, because the I, remember, the I can get outside the mod, right? So it becomes m to the power totient of n mod n, which is 1. 1 to the power I is 1. Okay? So this will lead to a 1. What is the condition here?
They are coprime,
Huh?
They are coprime.
They are coprime. By the way, this condition is neglected in many public cryptography books. They don't even mention that condition. Why, ba? No? It is reversible. It has to be reversible. It has to be reversible. But this condition, it is necessary for this theorem to be valid. Right? So the question is, why do we neglect that condition? And practically, is it achievable easily or not? Okay? Actually, the answer for both questions is the same. Go ahead.
What I meant is that in Fermat's theorem, which is Euler's generalization of Fermat's theorem, so the n is to the power of p minus 1, which says that it's equal to 1 with the mod of p.
Mm-hmm.
So there is no condition of coprime in Fermat's theorem.
In
Fermat's theorem.
Okay. I'm not aware of this.
I mean, this Euler theorem is generalization of Fermat's theorem.
Okay. Okay.
So
This
Fermat's
Euler theorem is a generalization of
Fermat's theorem.
theorem. Okay, which says what?
Which says that in your case, n to the power of p, which is your prime number that you selected, p minus 1, is equal to 1 mod of p.
Is equals to 1 mod of p, which is 1, yani. Is equal to 1 mod p, which is 1.
Yes.
Okay.
P minus 1.
Okay.
And your message. Or let's say some.
You mean like if the message to the power of any prime number?
Not any prime number. The prime number you selected.
The prime number I selected, which is E.
You selected P and Q, right?
P and Q, okay.
So let's take P.
Okay.
So P minus 1.
P minus 1.
Is equal to 1 mod of P. As I remember.
That cannot be, well, you have to put mod here as well. Yeah, it cannot be, it's not exact. It's not exact. But
It's not equal, it's the...
It's imperfect, yeah. Yes,
Congruent. Yeah.
exactly. I was missing the English word.
congruent? What does it mean?
The three lines.
3 lines instead of 2. 2 is equal, 3 is congruent.
Congruent. Yes, like this
أيوه.
is equivalent to 1 mod p. That's beyond my my background. Practically, I can get this condition very easily. Why? Because remember, these are 300 or 400 digit numbers. Okay? I can get this condition easily because m can be any number in the order of 300 or 400 digits, right? In order for this to become true, remember that n is only factorized as p and q only, which means that these are the only two numbers that are not supposed to happen in m, right? If these two numbers are not factors of m, then this GCD can be achieved easily, because only you have these two numbers that are factors of n, okay? So in practice, m has huge amount of degrees of freedom that makes this condition valid. So practically it can be achieved very easily, okay? Because the only two numbers that factorize n is p and q. So if p and q are avoided, then m can be any number, okay? طبعا even practically, nobody actually says that even if that condition is not valid, the theorem is not, this number is not 1. It could be 1. We don't know. But in order for the Euler theorem to be valid, this condition has to be valid, okay? But in practice, this can be achieved easily, okay? Which means that the reversibility of this algorithm is perfectly possible. And again, the robustness of this algorithm is coming from the fact that you don't know p and q, therefore you cannot calculate easily the tangent of n. Okay, that's the main issue. مش احنا قلنا because we said that any number, let's say 16 mod 3, for example. Okay, what is this? What is this number? Make it easy. What is this? 1. Okay. Why? Because 16 is in fact 3 times 5 plus 1. That's what I did. So when we say that we select D such that in D, E mod the tangent of n equals to 1. So this means DE equals to any number, any integer number طبعا, multiplied by the tangent of n plus 1. So that's exactly what I did. That's it.
Okay, you say that's equal 1.
Yes, because this is equal 1. Because 1 here is the remainder, right?
Yes.
Okay. So D times E is any multiplications of the tangent of n, but at the end there's plus 1. The remainder has to be 1. Right? Yeah, so that's what I did. Okay? So we can talk about a very small example. Okay? So in that case, here n is 187. Can you guess what P and Q are? يعني can you do it visually كده quickly? Remember, this is a very low number. Huh? This is very, very low number. It's a small number. So let's imagine that if you have...
Multiplication of two powers?
Yeah, it's a multiplication of two prime numbers.
I think it's 13 times 17, I think.
أنت بتغش.
No, I just...
You remember maybe he remembers that from the information security course.
Yeah, it's wrong.
Yes. So يعني what I mean is, even with that small number, it's not to be guessed easily.
Yeah.
So let's imagine if it's like 300 digits or 400 digits. It's not an easy job.
Yeah.
But if n is 187 and e is 7, so if we take a message, if we take a plain text message, which is this converted to a number, and it happens to be 88, so 88 to the power of 7 mod 187. Remember, the answer here has to be less than 187. We know that, طبعا. Okay. So that's basic. So the answer is 11. So this is the ciphertext. If we get the ciphertext and we use 23 is the D. Okay? And which means that, remember here, if we know the quotient of n, which again, in order to know it, we need to know what's P and Q, which until now we don't know it, right? Even with that low number. Okay, so we can sort of guess this 23 from the 7, which is not easy, because 23 is the multiplicative inverse of 7, okay, with respect to the quotient of n. So good luck, انت اصلا you don't know what's P and Q are, you don't know what's the quotient of n, and therefore you cannot guess the 23 easily. But assuming that we get this information, we will now learn how to calculate D systematically using the Euclidean procedure, or the Euclidean algorithm, or the extended Euclidean algorithm. We'll talk about that. So if we have D, so at the decryption side, if we say 11 to the power of 23 mod 187, we will get 88, which is good news, because then it's reversible and we can get the plain text. So that's all good, but that's, again, internally, some condition have to happen in that case. So that's بقى. So that's an example of how we go through calculating the public key and the private key internally inside the machine. So the previous example was based on the fact that P was in fact 17 and Q was 11. Did we get this? Visually, it was for us it was not an easy job. But now, if you multiply 17 by 11, okay, now it's clear. But once you know these two numbers, everything else becomes systematic. And of course, the RSA is based on the fact that these two prime numbers are not known. And remember, these two prime numbers are again like 300 digits or 400 digits. So to compute n, in that case, it's 187, which means that the quotient of n is 16 times 10, which is 160, which happens to be the number that we just tried. So 160, so we need to select a number, E, which is relatively prime to 160. And remember that here we have multiple choices. Remember, 160 was 2 to the power 5 times 5. Okay? So anything that has no factorization, neither 2 nor 5, is possible. Okay? So we have multiple choices for E. But we do not have multiple choices for D necessarily. We could have multiple choices for D as well. So we select E such that E and 160 are relatively or coprime. Okay? So, okay, so we need to determine بقى D, which is the multiplicative inverse of E with respect to the totient of N. Okay? So, assuming that E is 7, okay, where 7, of course, it is co-prime with the with 160 because it's not 2, it's not 7, it's not 2, it's not 5. So it's easily co-prime. So now D, okay, is the multiplicative inverse of E when it comes to the totient of N, which is 160. So D happens to be 23. How did we get this? We will see now how we get this. It's not, you could try multiple numbers and get it, but we will know now how to do it systematically. Okay? And now the public key is this, of course, which is N. Remember N, huh? Not the totient of. So after all, you do all this calculation, you put the public key as totient of N, which really makes the algorithm useless. Yeah. Don't do that, huh? So N is part of the public key, and the private key is 23 and N. Okay. So now we come to the Euclidean algorithm, which Euclidean algorithm itself is used to calculate the greatest common divisor between any two numbers. Okay. So that's number one. Number two talks about the extended Euclidean algorithm, okay, which is the reverse engineering of the Euclidean algorithm, which is typically used to calculate the multiplicative inverse. Okay? So the greatest common divisor between any two numbers comes from the fact that if we assume that 160, we take the bigger number, and then we say 160 is a linear combination of 7 with some remainder. Okay? So as long as it's a linear combination of any integer replication of 7 with any remainder, this greatest common divisor is reduced to the greatest common divisor of this 7 and the 6. Okay? So as long as the 160, which is here, it's an integer linear combination of 7, okay, with any remainder. Okay? So we take the 160, we remove all the integer linear combinations with respect to 7. And the remainder stays in the greatest common divisor and becomes like this. Okay? So the greatest common divisor of the big number is reduced to a smaller number, which actually is the remainder of dividing the 160 with the 7. واضح كده؟ Okay. طيب, so again, we do the same here. So the greatest common divisor of this is actually the 7. The 7 is a linear combination of 6 with a remainder of 1. Okay? So the greatest common divisor of the 7 and the 6 becomes the greatest common divisor of the 6 and the 1. Okay? Which is what is the greatest common divisor of 6 and 1? Is 1. All right? So that's systematic. Right? So this is a systematic way of getting the greatest common divisor of two big numbers by the process of reduction. Okay? So we reduce the big numbers into smaller numbers step by step until we get to a greatest common divisor that's easy to guess or easy to calculate. Okay? These steps, although these two numbers we can do it maybe in an easier way, but these steps are very important. Why, بقى? Because then if we do the reverse engineering of this, okay, we can always calculate the 1, okay, here, based on the fact that this 1 is actually 7, okay, plus 6 times minus 1. Why do we do this? The 1 here is the 7. Sorry, in order to calculate the multiplicative inverse of the 7, right? When it comes to 160, because we need to find D times E mod the 160 here, okay? And we need to make this equal to 1. صح? This is what we want. Here E is 7, right? So we need to calculate D. Okay? So the extended Euclidean algorithm is made for that purpose. If we know the 7, we need to find the multiplicative inverse, okay, such that when we multiply this by 7 mod the 160, it becomes 1. Okay? So this means that the 1 can be actually we say that DE equals to some integer I times the 160 plus 1, right?
Yes.
Which means that if we get this on the other side, it becomes the 1 becomes DE times 160 times minus I here, right? So this is like some minus I multiplied by the 160 here, which we don't care about. We don't care about the I. What we care about is this number. We need to calculate what this number is. Okay? Because this is the multiplicative inverse. Okay? So that's what we need to do. So the extended Euclidean algorithm is made for this. And the systematic steps are based on the fact that we go from the greatest common divisor, okay, and we try to do reverse engineering by saying that this 1 can be a linear combination of certain numbers based on the 7 and the 160. Okay? So how do we do this? So we start from where we ended here. Okay? So we say that the greatest common divisor of 6 and 1 is 1. This means that the 1 is in fact from here. The 1 is in fact 7 plus 6 times minus 1. From here. Okay? So once this number becomes 160, we stop. And the number here becomes the multiplicative inverse, which is D. You don't seem like you're excited about this. You don't seem like. Yeah. It's okay. Yeah, maybe for you it's like a boring.
No, it's not boring at all. You are explaining it very well.
Yeah. So, but maybe you took it before, but we have to go through this because, okay. So we do the reverse engineering. So the here the 6 from here, from this equation here, the 6 is a linear combination of the 160 and the 7 and the 23. Okay? So we take this here. Okay? So instead of the 6, we put the 160 times 7 times minus 22. All times minus 1. Okay? So now we have 160 in the equation, which is good news. Once we have 160, we need to calculate this based on 160 multiplied by a number and the 7 multiplied by a number. Once we have this, then we stop and say whatever is multiplied by the 7 is in fact the multiplicative inverse. Okay? And that's easy because here we have minus 22 times 1, okay, multiplied by 7, and we have 7 here, right? So it becomes 22 plus 1 multiplied by 7, which is 23. واضحة؟ تمام? Multiplied by 160 times minus 1. So now we achieved what we want. We have the 160, and whatever is multiplied by the 7 is the multiplicative inverse. Easy? It's easy. You just do it once or twice, it becomes very easy. Okay? So the Euclidean algorithm is used to calculate the greatest common divisor between any two numbers, whatever big these two numbers are. And that's good news because we have usually big numbers, right? But when we do it recursively, we can do that using a simple program. We can reduce it to smaller and smaller numbers, so we can calculate the greatest common divisor between any two numbers. So if the greatest common divisor happens to be 1, then we can achieve the multiplicative inverse using the extended Euclidean algorithm by going backward. ماشي كده؟ So D becomes 23. And that's what we have used for the example. Okay, so that's RSA. I hope you absorbed that. Now, Diffie-Hellman is fundamentally different. Again, it's based on some math, but the fundamentals of Diffie-Hellman is totally different from RSA. Okay, so Diffie-Hellman first, it's called first public, not from me, first published public key algorithm.
Which is true, first published.
First published, yes. Okay, so that's accurate. Okay. So a number of commercial products employ this key exchange technique. So as we will see later, just the fact that this is only used for key exchange doesn't mean that it's obsolete or deprecated or something. It's still being used in many products. The purpose of the algorithm is to enable two users to exchange a secret key, and we'll see. We'll see how this is done, because Diffie-Hellman is not necessarily, the reversibility is not necessary in that case. Although you will end up with the same key, which is it's fundamental, we have to have the same key on both sides, but it's not meant to be reversible. So this depends on the effectiveness of this Diffie-Hellman is based on another fundamental theory, which is totally different from RSA. This is based on the fact that the calculation of the discrete algorithm is mathematically difficult. So what is that discrete algorithm?
Logarithm.
The logarithm, yeah, we know that. But the discrete algorithm, the discrete logarithm, and I said algorithm.
Yeah, logarithm.
So I'm sorry, wallahi, I took antihistamine pill. It's actually making me a bit dizzy. So sorry about mispronouncing some words. I'm just imagining people online, they are, mostly they are sleeping. So the discrete logarithm is as follows. So if I tell you that, let's start very simple. So if I tell you a to the power x equals to b, so what is x? Yeah, so x becomes a log b, okay, divided by log a. That's easy, right? Right. Okay. So if I tell you a to the power x mod n, can you calculate that? Well, yeah, it's easy. I can calculate it using the calculator, using some factorization, using some multiplicative property. I can say that this is b. Yeah, I can do that. Okay. I can do that. Okay. So if I give you x, I give you a, I give you n, all of these. You can calculate b? Yes, very confidently, right? So what if I give you b, okay, and I give you n, and I give you a?
But you don't give the x.
What is x? هتقول لي I can do logarithm like this. Haha. Unfortunately, you have mod n. This complicates the whole thing. So now, if I give you b, n, and a, all of them, and I tell you calculate x, it's a very mathematically intensive job. Okay? It's numerically, you probably have to do exhaustive search. Imagine بقى if بقى, because that's another condition based on which Diffie-Hellman is based. If A is a primitive root of n, what does that mean? This means that if A is a primitive root of n, this means that for each exponent to A, okay, you will get a different value of B. Because remember, that's not necessarily true. Generally, if I give you any number to the exponent of x, let's say x is 1 and x is 3, okay? You may in fact get the same answer, right? Because this is mod n, right? Because this is mod n, so typically you could in fact end up with the same answer. But this is about the condition. If A is a primitive root of n, the number that you will get on the other side is always different. For each value of x, for each integer value of x. Okay? Where x, by the way, x is less than n minus 1. Okay? This means what? This means that for each value of x, we always get a unique number every time, which can be used for collision resistance. So it's like this is the message. So if you use the exponent of the message with respect to x, for each value of x you get a different answer. For each value of x you get a different answer. Okay, this means that A is a primitive root of n. Using any permutation, it may be that A to the power 1 mod n is 300, and A to the power 2 mod n is 1, and A to the power 3 mod n is 400. Doesn't matter. Okay, any permutation, but when you look at these numbers, they are all unique, they are all different. So in that case, we call A is a primitive root of n. Okay? This is a condition for Diffie-Hellman. This is a condition for Diffie-Hellman, that for each value of x, you have to achieve a different value for B. ماشي كده؟ Okay? Okay. So based on that, let's see the algorithm. The algorithm is based on the fact that now Alice and Bob, they share two numbers, Q and alpha. Q and alpha. Such that alpha is a primitive root of Q. This means that alpha to the power of any integer number mod Q will always lead to a different number every time. Okay? طيب. Very fundamentally very, very important here. Q and alpha, are they shared between Alice and Bob? Yes, that's different from RSA. Both of them, they have to have the same alpha and Q. Because remember here, it's not meant to be used for encryption here. It's not meant to be used for encryption. And it's based on the fact that what's difficult to achieve is not about alpha and Q, it's about X. It's about the exponent itself. This is what's hard to achieve, what's hard to get mathematically. Okay, so alpha and Q are to be shared between Alice and Bob. Okay, so Alice generates that exponent locally. And we are comfortable because of the fact that alpha is a primitive root of Q. For any exponent of X, we will achieve Y at Alice. Okay, which is not necessarily the same like Bob. Okay, it's not necessarily the same. We're not meant to be irreversible in that case. So Alice selects any arbitrary XA, okay, such that XA is less than Q. Because we said that it has to be less than Q for alpha to be a primitive root of Q. ماشي? And then we achieve Y. Y is alpha to the power X mod Q, which is YA. Okay? So YA is based on XA. And if you use alpha to the power XA plus 1, you will achieve a different YA. صح? Because again, alpha is a primitive root of Q. ماشي? Okay? So I will not, of course, share XA. I will share YA. Because again, we said that for this equation, if I give you YA, alpha and Q are shared, and I give you YA, can you guess XA? Bob cannot even guess what XA is. It's a very intensive job. And he doesn't need to know this. Okay? So I give Bob YA, alpha and Q are shared. I give YA. Okay? Bob will do the same. Okay? He will use local XB. It doesn't matter where XB happens to be equal to XA or not. It doesn't matter. Okay? And we will use XB and we get YB. And then YA will be shared, YB will be shared. Okay? Once we do this, now Alice will say, now we take YB, we use the same exponent we used before, okay? And mod Q, we will reach to a number. We will reach to a number. We don't know what this number is now. Eh? XA, this is Alice, huh? Alice selected XA before. So XA is known to Alice. It's not known to Bob, but it's known to Alice. Okay? So this is XA. We take the message coming from Bob, we put the exponent XA, we put mod Q, we come up with K. Okay? If Bob does the same using YA, okay, the good news is the answer will also be K. So both of them, they happen to generate the same number, even though neither of them select or know what is the exponent selected at Bob or Alice. Okay? So the good news is that both of them, they happen to reach to the same number. And the condition here is that alpha has to be a primitive root of Q. طبعا the proof that this will lead to the same like this is very easy. If we say alpha to the power xb mod q, okay, which is this is YB. YB is alpha to the power xb mod q, right? This is YB, right? This YB is here. So if we substitute YB from here, so YB becomes alpha to the power xb mod q all to the power xa mod q. Okay? So using again the multiplicative property is very important here. So it becomes alpha to the power xb times xa mod q, okay? And then, now we reverse. Instead of xb times xa, it becomes xa times xb. Right? So if we reverse it, we actually come to ya. So it's as if we have ya to the power of xb, which is the same here. Which means that whether we start with ya to the power of xb of yb to the power of xa, both of them will lead to the same number. Okay? Okay, so this is used for sharing a number securely. So again, the main essence here is that neither Alice nor Bob nor any attacker طبعا can guess what XA is or XB is. The robustness comes from here. Okay? So based on that, the Diffie-Hellman is robust in terms of key exchange. Type. Is it proof against? So this is proof against the eavesdropping attack. Eavesdropping attack. If you get YA, YB, you know alpha. By the way, you know Q. You have YA, you have YB. Yani you do whatever you want, you will not be able to guess XA or XB. This is the most important thing. So this is proof against the eavesdropping attack. That's good news. The bad news is it's not proof against man in the middle. So we'll see how this is bad on. طبعا يعني why طبعا there was a question يعني someone asked me before so how can we select alpha and q?
Yeah, how can share them?
لا, sharing is fine. Sharing is fine. How can I select alpha and q such that alpha is a primitive root of q? There are lookup tables for this. You don't have to يعني there are يعني millions of these combinations that you can select whatever. يعني there are some lookup tables that speed up this process. You don't have to really calculate alpha and q such as alpha is a primitive root of q. يعني, again, these numbers are 300 digits. Okay? But there are some techniques for this. There are some lookup tables to speed up this process. يعني. ماشي? So when we say alpha is a primitive root of q, so for example, 3, which is alpha, is a primitive root of 353. This means what? This means that if we put 3 to the power 1 mod 353, that's a 3. If we put 3 to the power 2 mod 350, that's 9. Right? And again, here we start, after some time, we start to have here number which is more than 353, but still the number we achieve here, as you can see, is always different. You cannot have two numbers here that are the same. That's the condition for alpha to be a primitive root of q. واضح? And these numbers can be in any sequence. Huh? They don't have to be in a specific sequence. Okay? They can go up and down. Doesn't matter.
Is there a table or rule if you want to dictate the size of the secret key that is generated in the end when you are selecting Q and alpha? Is there some relationship where you can say Q is this big, alpha is this big, or even when you are choosing XA, for example? In the end, I want to generate a key of this size.
I'm not aware of any, to be honest. The only thing I have come across is that again there are lookup tables for يعني these combinations of numbers with typical sizes. There are many lookup tables for these types of combinations. But to start from, let's say, a Q with a specific length, is there any indication of how you get alpha? I really don't know. I don't know if there is any.
But in the end, key, for example, you want secret key to be of certain strength. So
Of course.
So if you want to say I want 512-bit key in the end, which is going to be used.
Remember, the XB, it has to be less than Q.
Yeah, but that's what I'm saying. In the end,
Yes.
we get the key, the K
Right.
in your there. So we want K to be of certain size. Is there a method to dictate that by selecting Q and alpha?
Well, remember, K, again, is less than Q. So if you want to get K, like for example, in the order of 300 digits, okay, then you have to start with a Q that's in the same range, okay, so that K will be less than Q, okay, will always be less than Q, okay. So there is some kind of relationship between K, which is what you end up with, and the size of Q. So everything is actually dictated by how you choose Q. Okay? مفهومة كده؟ And of course, also K is dependent on the value of XA. Okay? Is also dependent on the value of XA. Because with different values of XA, you end up with different K. Okay? So K is in fact dependent, so that's a good question actually. So K is in fact dependent on two things, on the value of Q and on what you choose in terms of XA. So again, it's a good question because sometimes you get Q مثلا 300 digits, but you select XA such that you end up with K, which is much less than Q, which happens to be a smaller size, okay? But of course, there are some, again, what I heard is the best way is just to use, huge amount of lookup tables for this, so that, again, you select alpha and Q in such a way that not only alpha is a primitive root of Q, but if you use any value of XA, again, the number that you achieve is big enough, okay? طيب. So we'll stop here and then we'll talk about how the Diffie-Hellman is prone to man-in-the-middle attack. It's very easy. It's very easy. It's the same concept, but can we mitigate that? We'll see. طيب. So again, the good news is that the Diffie-Hellman attack is proof against the eavesdropping attack. So if you try to listen, you will not be able to guess XA or XB, in which case. But the problem is, if someone in the middle, and remember, alpha and Q are shared between everybody. Everybody knows it. So if any attacker Darth creates any XD1 and generates YD1 and give it to you, what you would naturally do is to give him YA. And in that case, both of you will generate the same key. And if you were to use that key later on, okay, Darth will be able to sniff the communication and break into the communication. So the Diffie-Hellman itself as a technique is not proof against the man-in-the-middle attack, because it's based on the fact that if anyone selects arbitrarily the exponent and give you y, you will give y based on the same alpha and q, in which case you will generate the same key and you will start to communicate using that key. So what will break this loop? So what do I need to have here in order to prevent man-in-the-middle attack?
Integration.
Integrity
check.
No, integrity has to do with the integrity of the message.
So
Integrity is protecting the message from being altered. But here, what I want to do is not necessarily integrity, but what I want to do is just to make sure that whoever is giving me y is a is an authentic person.
Non-repudiation.
Yeah, which has to do with message authentication and non-repudiation. Right. So we have to have some, not necessarily a token, any kind of authentication technique. We have talked about many of these before. So we need to have message authentication. Okay. So we need to have message authentication and or user authentication. We'll discuss in the next chapter that message authentication is different from user authentication. Okay? So what will break this loop is prior to getting Y, if you want to give me Y, that's fine, but embed in this Y who you are. I have to authorize or to authenticate who you are. Okay? واضح ولا مش واضح؟ Okay? ماشي كده؟ So Diffie-Hellman itself would not give you that. So that's why we said the only usage for Diffie-Hellman is to exchange the key. Okay? But exchanging this key has to be accompanied by a message authentication mechanism, which is not part of Diffie-Hellman. So message authentication, we can use the SHA with some encryption to authenticate each message coming from a particular user. Okay? So that's outside of the scope of Diffie-Hellman.
To break encryption, that is one time, even theoretical, it provides theoretical security one time path, right?
Mm-hmm.
So if instead of sharing both alpha and both prime number and the primitive root of it plus XA that we selected.
Not XA,
No,
YA. Yeah.
If there would be, and problem with the one-time pads is that they need to be the size of the message, right? So
yeah, pretty much, yes.
So if you would share between two, something like one-time pad that would contain only pairs of prime and the primitive root,
Mm-hmm.
right? They both know the order in which prime is used with which primitive root, and then
Alpha and Q and YA and YB are shared. Yes.
So you never actually need to share over the public channel the alpha and Q because they are already pre-shared in a type of the one-time pad, right?
No,
it's not real one-time pad. I'm saying if you
yes.
create the list.
No. What you are saying is that if I have YA and YB and they are shared, I don't have to share alpha and Q. How can you?
No, but I'm saying you're not sharing them over public channel in the sense of a one-time pad. Alice, here is the list of the primes and the primitive roots. Bob, here is the list of the primes and primitive roots. We are going to use them in this order. So.
Oh yes.
When
that's possible.
So
as long
in that
as
case, it would be impossible to do the man in the middle.
That's valid. Yani you have a combination of alphas and Qs, and there is some kind of agreement that we will use them in this sequence. Actually, this will have another level of security on top of because here, if we simply share alpha and Q with everyone, okay, then I have to do exhaustive search to get to XA. But what you are saying now is that I don't even have to share them through public channel. I can just have some agreement about how to use them from a predefined lookup table. Well, this is even more secure. That's good. That's even better. Okay, that's good. But again, even if you have alpha and Q, getting X is still a mathematically intensive job. And the bad thing here is that, again, this is not proof against the man-in-the-middle attack. So that's still valid. So you share alpha, you share Q, you share YB, you share YA. Okay? But anyone who would send you YD, YC, you will send the Y that corresponds to this, and in that case, you will end up generating the same key. Okay? And in that case, you will... But of course, if alpha and Q are not shared between everyone, but there is some kind of agreement about the sequence, then that's even
Plus, you don't use one-time pads, which are dependent, I mean, size of the message is dependent on the size of the one-time pads.
But you have like a
So in this
big
case, you would even
list.
overcome that problem of using these one-time pads, which are very complex.
Right. So what he's saying is that using or having this agreement based on the alphas and q's in certain sequence, this will in fact prevent the man-in-the-middle attack, because man-in-the-middle attack based on the fact that Darth knows the alpha and q. Okay, but I can create another level of security by even hiding alpha and q, but we have certain agreement or how to use them using this one-time pad or using some kind of lookup table with a specific sequence and so on and so forth. Okay? So that's what we need to discuss for DSS or Digital Signature Standard. Digital Signature Standard is a FIPS standard 168. FIPS طبعا is part of NIST. And it makes use of the SHA-1, okay? So SHA-1 on its own creates some kind of a hash of the original message, whatever that message is, right?
Yeah.
Okay? Is that on its own? This is for what? This is for checking what? For checking the integrity of the message, right?
Yes.
Again, by using the hashing, we protect the original message from being altered, right? So that's integrity. So the SHA or any hashing mechanism on its own is used to check the integrity of the message, okay? SHA on its own is not to be used for authentication. So we have to have something else other than SHA to guarantee the authentication or to do the authentication. So originally proposed in 91 and in 93 and 96, and it uses the algorithm that it's designed to provide only digital signature function. By this we mean only provide digital signature function, which means for data integrity, which means just the hash. Okay? So we take the message, we perform the hash, and the main importance of this hash is that it needs to have a collision resistance. So if you try to alter the message itself, the hash will be different, in which case I can detect this alteration easily, which means I guarantee message integrity. Okay? So the hashing is only for integrity. So unlike RSA, it cannot be used طبعا for encryption or key exchange. So DSS itself cannot be used for neither encryption nor the key exchange.
Mathematically impossible.
So in version 4 of this same standard, the DSS defines by a digital signature as the result of cryptographic transformation of data that, when properly implemented, provides a mechanism for verifying the authentication. So on top of this SHA-1, we have to take that hash and encrypt the hash with the private key or with a symmetric key. Okay? If we do that, then we stamp this hash with my identity, which is what we use for authentication. Okay? Okay? So FIBS specifies one of the three digital signature algorithms, which is the digital signature algorithm, RSA digital signal algorithm, or elliptic curve. So it does not specify any specific technique for encrypting the hash. You can use any technique to encrypt the hashes, but not the message, but the hash itself. Okay, so that's how it looks like. So at Bob hashes the message into the hash function using SHA-1 or SHA-2, okay, using a particular size for the hash itself, okay? After that, we use Bob's private key, okay, to encrypt the hash, okay, and then append it to the message. Remember, the message itself is not necessarily encrypted. Message itself is not necessarily encrypted. It's not. This is not for confidentiality. This is for these three. It's for the authentication, for non-repudiation, and for integrity. If we need to have a fourth one, confidentiality, then before doing this, we have to encrypt the message itself. So this technique fulfills these three conditions. Okay. So this technique fulfills these three conditions. So DSS is done for message authentication, for non-repudiation, because when Bob uses his own private key to stamp the hash, okay, and send it over, okay. Later on, let's say Alice is a bank, okay, and Alice will take this, and based on that, she will transfer $1 million to another account or something like this. Okay? Then Bob would say,
No.
I didn't do that. Okay? So in that case, Alice will say no. No one can sign this with the private key except you. Okay? So that's for non-repudiation. And of course, the hash itself is for checking the integrity. So the hash hopefully will have collision resistance. So if the message itself is altered in any way, okay, the hash will become invalid. So what happens at Alice's side is that Alice will take the message and will take the hash. And then, of course, the hash is encrypted. The hash is encrypted with the private key of Bob. So before we do the verification, we have to take this hash and decrypt it using Bob's public key. ماشي?
How does this help in preventing the man in the middle in Diffie Hellman?
Because then, if Darth is sending me a message,
Yeah, but
okay.
Diffie Hellman is for exchange of the keys, not for. So
Yeah.
during the initial exchange of the keys.
Diffie-Hellman is not here. It's not
I
in this
know,
picture.
but
Yes.
we were talking about the man in the middle and how to prevent it.
Right. So this will prevent it.
This will prevent it
This
if,
should.
if the keys are already shared, public and private. Right?
Oh yes, of course. Assuming that the Alice has the public key of Bob, which means that Alice can verify any message coming from Bob. Okay. So if the public key and private key are exchanged, then we can authorize or we can authenticate any message coming from Bob easily. Okay. So if Darth is sending me a message which is encrypted with his private key, okay, then if I have the public key for Darth and I decrypt it and I do this, I'm responsible for that. And this is supposedly Darth is not an authorized sender, in which case I should not actually have the public key for Darth in order to decrypt and get the hash. Okay, so in that case, Darth is not to be authenticated, but Bob or any other legitimate user can be authenticated if I have the public key for that particular user. Okay. So the hash is going to be decrypted using Bob's public key. So here I end up with two things. Here I have the decrypted hash, and I have the hash which is generated from the message using the same algorithm, which is either SHA-1, SHA-2, whatever. Okay, and then I perform that checking between the two, and that's it. Okay? So this will achieve these three conditions. As I said, confidentiality is not part of this. If we need to ensure confidentiality as well, then the message itself has to also be encrypted using either public key cryptography or symmetric key cryptography. Not Diffie-Hellman, okay? Not DSS, okay? Either public key or symmetric key. Public key or elliptic curve or symmetric key, we can use any of these techniques.
And then you need to share the symmetric key using the public private key. Then
Yeah, ما هو if you encrypt this message, and usually, by the way, the key that's used for authentication, as we will see بقى starting from next chapter, the key that's used for authentication is usually different from the key that's used for communication. Is usually different. Go ahead.
I mean, if you don't have time, you don't need to answer, but I was just thinking about this problem of the
Darth.
dart.
Uh-huh.
So,
All right. So, yeah, so that's it. That's pretty much it. So DSS is the technique that's used for digital signature, for integrity, for message authentication, but not to be used for general encryption. If we want to use general encryption, then we have to use another encryption technique, whether it's public key or symmetric key or elliptic curve or any other general purpose encryption. So this is the summary of what we discussed. I'm very reluctant to get to the next chapter because today was a little bit intensive in terms of math and stuff. So I'll give you some time to absorb that. Of course, for some people it's trivial because they have gone through it. But in this chapter, we have discussed the mechanisms for public key and message authentication. So we discussed message authentication codes. We discussed hashing techniques, how the hashing techniques should be collision resistant. This is very, very important. Okay, for that we discussed the SHA-2, and then we discussed the HMAC, okay, which is based on hash and message authentication codes. And then we discussed the digital signature generation using public cryptography, but then we discussed the public cryptography in more details based on the modular arithmetic equations, and then we discussed the DSS. So starting from next time, this is pretty much the end, because unfortunately we will not go through elliptic curve. It's not part of the book. So this is pretty much the end of discussing the security mechanisms and algorithms. So now we should be equipped with the proper tools, okay, to do different types of security services and applications. We know how to do message authentication. We know how to do encryption. We know how to guarantee message integrity. We have variety of techniques and algorithms. So starting from next time, we will use these techniques in different combinations to try to provide security services and applications in different network stack layers. So we'll start with the application layer. How do we provide security services and applications in the application layer? So we'll discuss that, for example, certificates, how we generate certificates, how we exchange certificates. Until now, we did not discuss user authentication. It does not require a sophisticated algorithm or mechanism. For user authentication, we use, like, for example, user ID and password, or use a token, as you said. So there's no sophisticated algorithm when it comes to user authentication. But we'll talk about the difference between message authentication and user authentication. How we generate certificates. How do we distribute these keys in application layer? How we mitigate attacks in data link layer. What is the difference between providing security services and applications in different layers? For example, in network layer, we have to visualize and keep in mind that we are doing routing. We have routers in the path. How do we provide security services when we have path end-to-end and we have to pass through different routers? For transport layer, for example, we provide security services and applications between two application endpoints. What does that mean? How do we provide the different security levels, confidentiality, integrity, things like that in the transport layer. What is the implication of this? So we'll start talking about that starting from chapter 4. So chapter 4 is the start of part 2 of this book, when we apply security mechanisms to provide applications and services in different layers, right? Part 3 is system level security, when we will discuss intrusion detection. So we have a big system network or some cloud or something like this. So how do we provide intrusion detection or firewalls and stuff like that? So that's what we will discuss in the next few lectures. Any questions?